Welcome to another organic chemistry video lecture. This one is on functional group chemistry. We're looking just at the reactions involving alkanes and alkenes. Our essential understanding, lots of words that basically say chemical reactions happen between organic molecules. Our objectives, we are going to write equations for the complete and incomplete combustion of alkanes. We're going to look at free radical substitution, also of alkanes. In the second half of the lecture, we're going to look at alkene reactions, addition, and polymerization. Then we're going to wrap up with a little compare and contrast reactivity of alkenes and alkenes using the tried and true bromine water test. So first, let's remind ourselves what even are alkanes and alkenes. Alkanes have no double bonds or triple bonds. Alkenes have double bonds. So I could have meth, eth, prop if I have all single bonds between my carbons. Fill in the octet rule with lots of hydrogens. This is going to be, again, 1, 2, 3 carbons, meth, eth, prop. This is prop, and because there are no double or single bonds, double or triple bonds, there are all single bonds. No double or triple bonds, we've got propane. If I take those same 3 carbons and I put a double bond in between them, I'm still going to fill in the molecule with hydrogens to fulfill the octet rule. But notice that this carbon has 2 bonds already here, so he only needs 2 more hydrogens. This carbon's got 1, 2, 3. He only gets 1 hydrogen. This guy gets that normal 3 hydrogens to fill out that octet rule. So we're going to call this guy still meth, eth, prop because I've got 3 carbons. It's prop, but because of that double bond, we're going to call it propene instead. Because this propane molecule is as full with hydrogens as it can possibly be, we're going to call it a saturated hydrocarbon. Propene is not saturated, it is unsaturated because it's missing some hydrogens. Notice that this guy C3H8, this guy C3H6, fewer hydrogens, not as many as possible. Because of that double bond, we're going to call it unsaturated. So let's look at some reactions of alkanes first. And we're going to start with combustion. For that combustion, we're adding oxygen gas. Oxygen gas is a reactant. The complete combustion of any hydrocarbons, let's stick with propane. We add some oxygen gas. The complete combustion of hydrocarbons like propane is going to produce carbon dioxide and water and energy. That energy will be in the form of heat and perhaps some light. We can balance this guy. I've got 3 carbons, so I need 3 carbons here. I've got 8 hydrogens, so a 4 in front of water is going to give me those 8 hydrogens. Now I have 4 oxygens here, 6 oxygens here. That's a total of 10, so a 5 here is going to give me a balanced equation. So the complete combustion of any hydrocarbon is going to produce carbon dioxide and water and energy. Memorize that. Incomplete combustion, where we have a little bit less oxygen available, what we're going to make that's a little bit different, instead of carbon dioxide, we're going to make carbon monoxide. This is bad. We'll still have some water, we'll have some energy in the form of heat and light. When we balance this guy, we will notice that we've got, instead of 5 moles of oxygen, we only need 3.5 moles of oxygen in order to incompletely combust this propane. So more oxygen is needed for complete combustion, a little bit less oxygen is needed for incomplete combustion, but carbon monoxide is bad. Sometimes we can also get products of just carbon in the form of soot. This also is letting us know that there was some incomplete combustion. The second kind of reaction that we're going to look at with alkanes is substitution. So let's say that we're looking at methane. So just 1 carbon in this guy. We can halogenate it and make it a little bit more reactive, more interesting, by adding that halogen group, halogenation, adding a halogen. So let's go ahead and add, maybe we'll add some chlorine to this guy. So what we're going to make in this substitution reaction is literally a substitution between the hydrogen and the chlorine. So I'm going to keep most of this molecule So I've got my C and my 3 H's, but that third H instead of fourth H, I can count. Instead of that fourth H, we're going to substitute that last hydrogen with a chlorine. And what we'll have left is that hydrogen that we took off when we substituted the chlorine and then that other chlorine. So again, we're just going to trade this hydrogen and this chlorine. So instead of having carbon with 4 hydrogens, we're going to have carbon with 3 hydrogens and a chlorine. We're going to take that hydrogen and plop it onto the other chlorine to make HCl. So this is a substitution reaction because I am literally substituting one atom for another. We're just trading spaces. So what's kind of interesting about these substitution reactions is that they don't happen very easily by themselves. In order to get these substitution reactions to happen, so that we can trade a hydrogen for a halogen, we need to form some free radicals. And these free radicals are going to be formed by homolytic fission. So these different fissions, or sometimes we call them fragmentations, can come in 2 varieties, heterolytic and homolytic. Hetero means different, homo means the same. Let's say that I've got this bromine molecule, 2 electrons are being shared. If when this molecule splits, both of the electrons that are in the shared pair go to one of the atoms and not the other, the result is going to be things that are different. So I don't have the same particle here and here. Instead, this guy's got an extra electron, it's negatively charged. This guy's down an electron, it's positively charged. So this is why it's heterolytic. We did not split those electrons evenly. I've got different stuff being formed. However, if those electrons that are being shared in that bromine molecule, if one goes to one of the atoms and the other one goes to the other atom, and then I have 2 bromines that are the same, homolytic, they're the same, each of them has 1 unpaired electron, which is super, super crazy reactive. These are our free radicals. These are what we need in order for the substitution reactions to occur. But that's not the only thing we need for these free radical substitutions to occur. So that homolytic fission, that splitting, is going to be the first step. The first step is known as initiation. So we're going to take lots of big, bright, crazy light energy. We're going to split that, in this example, chlorine molecule into 2 chloride free radicals. So this little dot here is showing us that we have that unpaired electron. That dot tells us this is a free radical. So I take that Cl2, I split it into 2 free radical chlorines. Now this crazy high energy unstable guy with this extra electron is going to go and attack whatever our hydrocarbon is. In this example, I've got methane. So chlorine is going to come and attack. It's going to knock a hydrogen off. That hydrogen is going to grab onto the chlorine, and then what we're left with is CH3, because one of those hydrogens is now with the chlorine. So CH3 has an unpaired electron, so now I have a methyl free radical. That methyl free radical is going to go find another chlorine molecule. So that free radical, there should be a dot there. So that free radical methane, that methyl free radical is going to go and attack a chlorine molecule. It's going to grab one of the chlorines. And so now I have chloromethane. The other chlorine is now a free radical. And guess what happens? This guy goes and attacks a methane. We make HCl, and that methyl free radical attacks another chlorine, and we get chloromethane and another chlorine free radical that attacks the methane, and we get a methyl free radical that attacks the chlorine, and we get a chlorine free radical. And you can imagine that this just keeps going and going and going. We call this propagation because we are propagating lots and lots of product. At some point, we're going to start to run out of those hydrocarbons. So when we're starting to run out of that, in this example, methane, then what happens is those free radicals go and find each other. So we're going to have, in that termination step, we might have 2 free radical chlorines that find each other and make a chlorine molecule. We might have a chlorine free radical and a methyl free radical that make chloromethane. We might have 2 methyl free radicals that find each other and we make ethane. So this is termination. Those free radicals simply find each other. We're not forming any new free radicals. Instead, we're just pairing up free radicals to make not free radicals. So this is the set of steps: initiation, propagation, termination. In free radical substitution, memorize this. So once again, we have initiation is going to be that homolytic fission of some halogen where we need lots of big light energy UV radiation. Propagation is where we're forming lots and lots of more free radicals when a free radical attacks something. And then termination is when those free radicals just kind of find each other. They pair up so that we have fewer free radicals. All right, so now we're going to move away from alkanes and talk about alkenes instead. Alkenes are quite a bit more reactive than alkanes because of those double bonds. We're going to look at two specific kind of reactions: addition and polymerization. So first up, addition reactions. So addition reactions, literally, we're adding stuff. Hydrogenation is an example of an addition reaction where we're adding hydrogens. So this is ethene, because we have two carbons, ethene. Sometimes it's also known as ethylene. You can call it either one. Both are correct. So ethene, ethylene. So when we add a hydrogen, when we hydrogenate this ethylene, what we do is literally break apart the double bonds and we add those hydrogens in. We add the hydrogens, and so those hydrogens that used to be here are now here. We added them to the ethene molecule and we made ethane. So we broke that double bond that used to be here, broke that double bond and added in the hydrogens. This is an addition reaction because I'm literally adding stuff. Addition reactions are different from substitution reactions. So alkenes, we have addition reactions. So let's say that we have we'll go back to ethene. If I add a chlorine, what's going to happen is we're going to break that double bond and those chlorines are just going to add themselves to the molecule. So we could have perhaps dichloroethane. So 1,2-dichloroethane is a potential product. In order to make this happen, we just need to add some chlorine. So the chlorine is attracted to all the electrons in this double bond. We're going to have this addition reaction occur. Alkanes, we cannot add anything to the alkanes because they're already saturated. So let's say that I had ethane, the alkane, and I added some chlorine to it. This is going to be a substitution reaction where I'm going to trade one of the hydrogens for one of those chlorines, and then we could make chloroethane, and we would have HCl as the other product. Notice that there's only one product here because I added the chlorines to that ethene molecule. Here we're trading places, and so here is the result of those traded places. This reaction, the substitution reaction of the alkanes, requires energy in the form of UV radiation. This reaction with the alkenes is quite spontaneous, so we don't need to do a whole bunch to get this to go. We can also have these addition reactions with steam. So let's go back to ethene, which you can also call ethylene. And let's say that we're adding steam. So I'm heating this up with lots of water, so big heat. So that delta over the yield sign means that we're adding heat. Lots of heat energy. What's going to happen is the water is going to break apart into hydroxyl groups and hydrogen ions. The hydroxyl group is going to add itself in here. The hydrogen is going to also add itself in here. We're going to form no double bonds because we break that double bond when I add the other pieces. But now we have carbon with those three hydrogens. I have carbon with two hydrogens, and then we have that hydroxyl group. So we added that hydroxyl group. So now I've made an alcohol. So in this addition reaction with water or steam, the hydroxyl group will come in and jump onto one of the carbons. The hydrogen will go onto the other carbon when we break that double bond. We go from double bond to single bond, and then we end up with ethanol. Now we're going to look at polymerization. So polymerization is another reaction that happens with alkenes, not alkanes, only alkenes. Polymerization is super, super cool. So little bits of vocab first. Mono is one, di is two, poly is many. So we could start with a monomer. This is called polypropylene. Because each of the repeating units, so notice that this piece kind of repeats over and over. So each of these monomers, these repeating units, are 1, 2, 3 carbons. That's prop. And because we have many of them, it's polypropylene. So one of our plastics, polypropylene, we use this for food containers and all kinds of cool stuff. So one of those repeating units is the monomer. Di is 2. So if I were looking at 2 pieces, 2 of the repeating units, that would be considered a dimer. Then polymer is the whole entire thing. So let's look at how these polymers can form. So I'm going to take my ethene or ethylene molecule. This double bond is going to break. I have another, I forgot my C, another ethylene molecule next to it. This double bond will break. The double bond is going to break and flip out to bind to the next ethylene molecule. Same thing over here. I have another ethylene molecule, ethylene or ethene. That double bond is going to break into a single bond and then flip around to bind to the next guy. And then we just have this crazy long repeating polymer of these ethylene or ethene molecules. So here's one, and here's the next one, and here's the next one, and we just keep going and going and going. Sometimes we write it out with the monomer in parentheses, and then this number n is some very large integer. So this is the number of repeats of the ethylene or the ethene. We're going to call this polyethylene. Polyethylene, also known as PE, it is the most widely used plastic in the whole entire world. It's like 100 million tons of this are made. Every single year we have low density polyethylene and high density polyethylene. A third of all toys in the whole entire planet are made out of high density polyethylene. So if I ask you for the economic importance of polymerized alkenes, you're just going to be like, plastic, all the plastic in the whole entire world. So here I'm going to have us practice forming a polymer from the monomers. If I have this monomer and I want to polymerize it, first off, I want to name this guy. So I've got 1, 2 carbons. That's going to make it ethene because of the double bond. I've got a chlorine in here, so it's going to be chloroethene, chloroethene. I would actually count that as carbon number 1 since it's on the chlorine, right? So 1 and 2 chloroethene. In order to polymerize it, what I'm going to do is put more of these guys next to each other. So I'm going to have C, 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 L, H, H, and H. I'm going to repeat this chloroethene molecule, but I'm going to take away the double bond. I'm going to use the other part of the double bond to make the connection to the next molecule. So then we'll repeat the CH2, CClH, and then I'm going to do it again. CH2, CClH, and then we're going to keep going, and we'll show that it keeps going with these lines that attach to nothing and everything. So this would be a polymer of chloroethene. We sometimes also call it polychloroethene. Sometimes we also call it polyvinyl chloride. Polyvinyl vinyl chloride, better known in Lowe's and Home Depot as PVC. So PVC is this super cool plastic, polyvinyl chloride, polychloroethene. Good? Good. So we're going to take one last little look at polymerization. This time I'm going to start with the polymer, and I want us to figure out what is the monomer that makes up this polymer. How we do that, we just find our repeating units. So I notice that I've got CH and a phenyl group and then CH2. And then we have CH and a phenyl group and CH2. And then we have CH and a phenyl group and CH2. So here is our repeating unit. In order to figure out the monomer, I'm just going to take that single bond and put it back into a double bond. So what this guy looked like before it was polymerized, I have C with an H and that phenyl group. And then we're going to double bond it to carbon and 2 hydrogens. Carbon and 2 hydrogens. I'm going to call this, because I have meth, eth, I've got eth, double bond ene. That phenyl group is going to make it phenylethene, phenylethene. Kind of cool. This stuff, polystyrene, also is a plastic, but I can make it kind of foamy when I make it, and that makes this styrofoam, which is super cool. So again, if I ask you a question about the economic importance of polymerized alkenes, you're just going to tell me about plastic and styrofoam. And to wrap up this video lecture on alkane and alkene reactions, we're going to look at this super cool thing called the bromine water test. Let's say that you were in a lab and there was like a bottle of stuff and the label fell off and you didn't know if it was an alkane or an alkene, and you wanted to figure out if it was an alkane or an alkene. It could happen, right? Labels fall off sometimes. What we're going to do is we're going to add this stuff called bromine water. So bromine water is literally just like bromine with some water. It's brown. So bromine in water is brown. Brownish red, if you will. So if I have ethene, an alkene, if I have an alkene and I add bromine water to it, we're going to have a spontaneous addition reaction. The spontaneous addition reaction will happen, and then, because I don't have any more Br2, because I have bromine instead in this molecule, we're going to go from brownish red to colorless. So we're going to go from, it was like this, but then it turned like this. It turned colorless. That tells us that I had an alkene that went through an addition reaction with that bromine. If, however, I have an alkane, like here I have ethane, if I add bromine water to my ethane, nothing's going to happen unless I add big UV radiation to make that substitution reaction occur. So we're going to have that substitution reaction occur only with big UV radiation. If I keep my reaction happening in the dark, not that you could see a color in the dark, but let's say that we were not in a well-lit laboratory, but in somewhat dark spaces, adding the bromine water to the alkane, nothing's going to happen. If there's no UV radiation, no reaction is going to happen. That bromine water will stay bromine water and it will stay brown. It will not turn colorless unless you turn on the big bright lights. Ooh, pretend like that's a big light bulb. Those big bright lights, and then that brown will go to colorless because that substitution, this substitution reaction, will happen with lots of light energy. Good. So again, if you want to figure out if you have an alkane or an alkene, add bromine water. If it spontaneously turns colorless, then you've got an alkene that just went through an addition reaction. If it stays brown, you've got an alkane that will only carry out that substitution reaction with the bromine if you've got big light energy. And objectives accomplished. We wrote equations for complete and incomplete combustion of alkanes. Remember that complete, we're going to make CO2 in water. Incomplete, we make carbon monoxide or maybe some soot and water. We looked at free radical substitution reactions with alkanes. This requires big UV radiation and homolytic fission in order to get it going. There were those 3 steps. We had initiation. Ooh, if I could spell. And then we had propagation, and then we had termination. Make sure you have those memorized. We looked at addition reactions with alkenes. These do happen spontaneously, no free radicals necessary. We looked at polymerization, and then we talked about bromine water. If you add bromine to an alkane in a dark lab, it's going to stay brown. If we add bromine water to an alkene, even in the dark, that bromine water will add itself to the alkene, and we will have a colorless product.